Hey everyone, Professor Dustin here, and this video is going to be a crash course in two-dimensional, three-dimensional integrals, so doing area and volume integrals. Of course, I'm interested in using these in physics, specifically in Gauss's law type problems, so I'm going to focus on planar situations, spherical situations, and cylindrical situations in particular, because that's how we're going to manage to handle Gauss's law, and I basically just want to give you just the essential information that you need to sort of understand and complete these integrations. So just to give you a sense of what we're shooting for here, a two-dimensional integral is like you have a function of two variables and you want to integrate that over some two-dimensional region. Say that you have this d here. So this function up here kind of represents, the top of the volume you want to integrate over, and then the sort of the bottom tells you where the bottom is. So you're actually finding the total volume inside this area d, where the top is like governed by that function. And you study this in calculus a little bit, you break these things into rectangles, and then you add up all the rectangles, and that gives you the area under the curve. Area under the curve is the idea that we're doing here, but of course area under the curve becomes a volume when you have a two-dimensional integration like that. So that's essentially what we're going to be doing. If you're thinking, oh, what possible application could that have? Well, one, you can come up with all sorts of different things in different areas. We're going to do it in Gauss's law, right, for electricity and magnetism. But like if you wanted to calculate the area of your house, for instance, the volume of your house. So your house is kind of squarish, but let's say your house actually had like an angled roof or something, something like that. And you wanted to find the total volume of that. Well, you could find the equation of the line that governs the angle of the roof, and then you can integrate that over some kind of like, in this case, it would be like the f of x, y. That would be the function that governs the angle of the roof there. And you would have the like xy coordinate system down there. Anyway, so finding the volume of the inside here, that could be an application of this. But of course, we want to talk more about like doing planes and cylinders and things like that. So let me tell you how to do these kind of integrations in as quick a way as I possibly can. So basically, we're talking about integrals like this, right? Where, like we've discussed in class, this dA would be like dx dy if you have some two-dimensional surface. And the function in general could be like some arbitrary thing of x and y. And so this case is actually easy, and in fact there are no tricks to this. There's nothing to do but just crank through it. If x and y are really in the function, meaning your function really is a good function of x and y, like I'm just going to pick a random one, let's say x squared plus y squared dx dy, then there's nothing to do but what we've done in the past, which is, put the integration ranges, let's say 0 to a for x, 0 to b for y, and just straight up do the integrals. There's nothing that you can really do except that. However, there may be some cases where, because of the form of the integration here, the problem actually gets simpler. So for example, let's pick something which is not a function of both x and y. So let's say we have a function which is just like 3x squared or something. We still want to do dx dy. We still want to integrate that function over an area, an honest to God 0 to a, 0 to b area. But it's not a function of y. Okay, well, we can almost do this in our heads, right? So the y doesn't depend on, and anything in here doesn't depend on y, so we can actually pull the y out, and so we can think of this as like two integrations that are multiplied times each other. dy, 0 to a, like 3x squared dx. And we could do them separately, and out here, all you get is an integration on y, which will be y limits 0 to b, and of course the answer there is just b minus 0, is just the total distance b. Now you still have to do the integral over here, but you are basically only taking a constant value for the integral there. So what have you done? So you actually took the area, so let's say we had the area here, and the x went 0 to a, and the y went 0 to b. So all you did is you noticed that the since this integrand, this 3x squared, didn't depend on y, it's actually easy to recognize you didn't have to do the y integral at all. You just got the answer b. So in fact, another way to think about this is you're changing this two-dimensional integral into a one-dimensional integral where you're sort of dividing the box up into slices. So instead of integrating both along x and y, you just integrate along dx, and then you set the y to be b. So the area of each one of these little rectangles there is b times dx. So you're saying the integral doesn't depend, the integrand doesn't depend on y, so who cares? Let's just get rid of that part of the integral, and let's calculate the integral of each of these little rectangles, just setting y to be b, and then integrating along x. So let me give you just a little bit more detail about how that looks. So I'm basically rewriting this integral to be the integral just on x of 3x squared, and then my dA, I'm going to write b dx. So that whole thing is now my dA, where I'm just saying, well, y is constant, so I'm just going to set it to be b the whole way and only worry about the x direction. So this is called integration by slicing. So by slicing, where you reduce your two-dimensional integral, which is this thing, into a one-dimensional integral just over the thing that you're integrating over. And so this is the basic trick that we're going to do for nearly all of Gauss's law. So let me do another example now with the cylinder. So there's a nice cylinder. Now in this coordinate system, the cylindrical coordinate system is going to have an r component, a theta component, and a z component. And so remember that the r is measured out from the center, the theta is measured around, and the z is measured up. And the 0 is typically like down there. So that's the coordinate system. Now let's think about a typical integral that we might do. Now I'm just not thinking about an arbitrary integral, I'm thinking about an integral for Gauss's law. So the real issue with Gauss's law is we often are trying to find the total enclosed charge inside of some region. Now sometimes that's super easy to do because we can just do like the density of the charge times the volume or something, right? But what if the density depends on r, theta, and z? What if it depends on where you are in the surface? So that means that you're going to have to do some kind of integral. So that means that the enclosed charge would actually be like the integral of rho dv. Now, it can be true that the rho depends on, anything, any one of these coordinates. In that case, you don't really have anything to do except go to a computer, basically, and do the calculation. Or maybe if it's simple enough, maybe you can do it by hand. The slicing technique I'm talking about, it really comes into power when rho only depends on one of the variables. And I'm going to tell you right now, the typical variable we're going to use is r. Because remember, we're doing Gauss's law, so there are certain symmetry conditions that we want to have on our problem. Specifically, we kind of want the electric field to only depend on the radius. We don't really want the electric field to depend on these other things. So typically, we'll have a rho which just depends on r. So actually, I'm going to set that rho of r to be the case. So rho is just going to be dependent on r. Well, so what does that mean? That means that we want to set up our integral to, instead of being a volume integral, the volume integral would be something like, dr, dz, d theta. Not thinking too hard, just saying we have 3 dimensions, so we need 3 little differentials. But only the r part is what we want to do. We want to do this slicing technique to get rid of the dz, d theta, and to think about, like, what is the area that is represented by that part of the integral. So the way we're going to do that is we're going to think about slicing up this cylinder into a bunch of annuli, meaning a bunch of like rings that have radius dr, means size dr, but this part is constant. And so that's pretty easy to do if I just make a circle like that and a circle like that. So that little chunk there is the size of the annulus dr. The whole length is some fixed length, right? Some fixed size, so I'm going to call that L. And then the theta just goes around. So what I want is the volume of one of those little rings there, which are sort of coaxial cables or something, right? So the way you do that is you take the area of a cylinder. That's going to be 2 pi r times the length, right? That's the area of a cylinder, and then you multiply it times the little annulus size right there, which gives you the total volume. So this is actually the volume integral here, dv. And again, I did that by slicing. Now it's a little harder to see the slicing in this three-dimensional example where you have cylindrical symmetry, but it's pretty easy to see that like it's just the cylinder is this thick cylinder like this, not a thin cylinder, but a cylinder with some thickness. An infinitely thin cylinder would have an area 2 pi rl, right? 2 pi times the radius times the length there. So in order to get a thick cylinder, I just need to put a dr in there to get my dv. Yes, there's some calculus that I'm skipping over here, but I'm trying to get to the answer as quickly as possible. So that's actually the correct formula for the volume. So if I have a rho, which depends just on r, I can put in that 2 pi r times L dr and just do the integration immediately. Let's do a concrete example. Let's say that rho of r is some constant a times r squared, right? I don't know, I'm just making it up. Let's say that that's the dependence on r. Well, then we throw this into the integral. Let's pull all the constant stuff out. I got a 2 pi. I got an L. I've got a constant there, A. So this integral is now r squared. Careful, there's another r there, right there. So that integral becomes an r cubed. So I got 2 factors of r from the dependence of rho, and then another factor from the r there. So that's an r cubed. Let me make that neater. Then the dr comes from right there, and I'm just doing this particular integral. Typically, you would do it right from like 0 out to some radius r, where the radius of the cylinder is a fixed r like that, right? So that's how you do this integral, and obviously that's easy. It just becomes 2 pi LA. R cubed becomes r4 over 4 between 0 and r, and that gives you your final answer to being 2 pi LA r to the 4th. Right. So that looks like kind of a crazy thing, but that's the answer if you have this particular setup for the charge density. Okay, so that's how you do the cylinder one. Let's real quickly jump to do the spherical one as well. Okay, so if I got some spherical geometry and I want to do the same thing, so again, the form of these things is, and of course in spherical geometry, I have 2 angles and an r, so the r is measured straight out from the center like that, and the 2 angles are usually measured theta down like that, and then phi around like that, so theta being from the North Pole and phi being from some arbitrary point going around the equator like that. So we want to do integrals like this to find the total enclosed charge times dv, and again the same thing. In principle, if rho depends on all 3 of those things, our volume will be something, and again I'm just sort of saying something like dr d phi d theta. Now if you know anything about spherical coordinates, that's not the right integrand there, but it's okay, we don't need it really, because again we're going to be mostly focused on things where the charge distribution just depends on the radius. So in that situation, we want our integral to be from 0 to, let's say, the radius of the sphere is r. And I'll write it as r, rho of r, and we'll do a specific example too later. But for the volume now, what I want to do is I want to think about, okay, this depends on r, so clearly somewhere in here I'm going to have a dr, but everything else is constant. So what happens when everything else is constant, when phi and theta are constant? Okay, you get a sphere of thickness dr. So that's going to be really hard to draw. I'm going to cut the sphere in half, so I get a hemisphere. There's my dr. And then the bottom half is like that. And of course, like, this is a half hemisphere, so it's like half a soccer ball with a soccer ball's thickness, right? So what I want to put here is actually I want to put the surface area of a sphere there, right? So I've drawn only half of it. The whole thing would obviously be 1/2 plus the other half. You know, something like that, where those are the 2 halves, and you add them up to get the whole thing, right? You get what I'm saying. There's a ring here too. Yeah, anyway. So I want to put there the total surface area of a sphere. Of course, the total surface area of a sphere is 4 pi r squared. So that's actually the volume element for a sphere, 4 pi r squared dr. You can write it that way if rho only depends on r. If it doesn't depend on theta and phi, then you get this very nice slicing expression for the sphere. So let's do the same problem that we just did, just to complete this. Let's assume let's assume rho of r is c times r squared. So then our integral becomes 0 to r, c times r squared. Our volume element is 4 pi r squared dr. Doing this integral means pulling out the constants. We got a 4 pi c is our constants here, right? Integral between 0 and r. And actually now, because the volume integral, the volume element has an r squared, and the charge density has an r squared too, we get an r to the 4th dr. And again, that's a pretty easy integral to do. That r to the 4th becomes r to the 5th. Divide by 5, put the r in, and actually I can write put the limits in rather. I can write the answer immediately. It's 4/5 pi c r to the 5th. So again, looks like kind of a strange expression. That's kind of because I just made it up, right? But actually, charge dependence like this is not so crazy. It's 0 charge in the center and gets bigger and bigger as you get outside. So it's not like a totally insane charge density, just a little bit made up. But anyway, the point is that this slicing technique allows you to write volume integrals like this as one-dimensional integrals. And one-dimensional integrals are things you know how to do from like Calc 1, right? And so this is typically always going to be our examples in this class, is we are basically always going to have charge densities that only depend on one variable. In fact, we are nearly always going to have just R as the variable because we always want to have the spherical symmetry that applies to Gauss's law. Spherical symmetry, cylindrical symmetry, planar symmetry that applies to Gauss's law. Okay, so I hope this crash course to volume integration using slicing has been helpful. Let me know if you need more information on this. It's just enough to get us through Gauss's law. So, okay, great. Thanks very much, and I will see you guys in class.